Okay, I guess maybe we can get started. Good morning, everyone. I hope all of you had a great vacation. Happy New Year, and welcome back to SNAPP. So we have an exciting lineup of speakers for the Spring 2021 offering of SNAPP seminar. And our first speaker today is Professor Guy Bresler. So let me start by introducing Guy. Guy is an associate professor of electrical engineering and computer science at MIT, and he's also a member of LITS, IDSS, and Center for Statistics. He received his PhD from ECS at UC Berkeley and his BS in ECE from University of Illinois at Urbana-Champaign. Guy's research interests are broadly in statistical inference and machine learning, and in particular, he aims to elucidate relationships between combinatorial structure, information structure, and computational tractability. Today, he's going to talk about reducibility and statistical computational gaps from secret leakage. Just a recap about questions. So if you have any quick questions as we go through the talk, please type them on the chat box. I'll keep monitoring the chat box and then pause Guy if there are any urgent questions. If not, Guy is going to have a short 1 or 2 minute break midway through the talk when you can have when you can ask questions, and then we'll have an elaborate question answer session at the very end of the talk. So it's all yours, Guy.
Perfect. Thank you so much, Sivateja, and to the organizers. It's terrific to be here. This is a community that I very much feel close to, and there are many friendly faces here I see in the audience. So it's great to see you. Hope you have had a decent start to the new year. So this talk is about computational complexity of high-dimensional statistics problems at large. And the real motivation for this talk is to try to get us to think a little bit about the relationships between problems as opposed to studying each problem in isolation, which is what is typically done in statistics and machine learning. So I should also say that in many ways, you guys are the perfect audience for this. You have exactly the right expertise to be solving and addressing some of these questions that we weren't able necessarily to address. So I'm sort of very hopeful that some of you guys in the audience get excited and start to think about these questions. So all of the things I'll talk about today are from a paper from last summer of my PhD student, Matt Brannon. And if there's any really hard questions, please email him. For the remaining questions, please do type in the chat, and I'll try to answer them as best as I can, and there will be a couple minutes in the middle, and obviously at the end. Okay, so I'm gonna start with just a little bit of an overview of what is the subfield you've been trying to answer, and sort of what's going on. So, sorry, I have this bar here that's in the way. All right, so high-dimensional statistics at large can be sort of in a caricature, in a cartoon. The question is, let's estimate some signal in random noise. And aside from an estimation question, we'll also be talking about a detection formulation where the question is there a signal, or is what I'm looking at pure noise? Again, so let's sort of go back and forth between detection and decision versus estimation, and it will be obvious in each particular case which one we're talking about. Okay, so to be a little bit more concrete, here's a particular problem that's gained a ton of attention in the last decade. It's called Sparse PCA, and this is the detection formulation in the spiked covariance model of Ian Johnstone. And so here's the problem. It's a simple hypothesis testing problem. You're given n samples, and these n samples are either from an isotropic Gaussian in d dimensions, or from a Gaussian that has a covariance matrix that's identity plus this little spike, theta times v transpose, and v is a k-sparse unit vector, meaning that it has k non-zero entries. It's unit vector, so its L2 norm is 1. Okay, and so you're given these n samples, and your goal is to decide which of these two is the case, and this is the sort of signal plus noise problem of interest. This is just one example of a problem among many, and we'll see some others. Okay, now in most of these problems, there are tons of parameters. That's one of the unfortunate things about this field, but you guys work with MDPs and things like this, so you're used to tons of parameters, so maybe this isn't a lot for you. But anyhow, D will be dimension, K is sparsity, the number of non-zeros in a vector, N is number of samples, and theta is some sort of signal strength parameter. In the sparse PCA example, it's the coefficient in front of the spike in the covariance matrix. All right, now the basic question that you might ask as an information theorist or a mathematical statistician is, well, how much data do I need? And one way to sort of visualize this question, to answer this question, is to plot in a figure like this, the answer, solvable or unsolvable. And so on the horizontal axis here, we have the sparsity growing polynomially. And so alpha here along the x-axis is the power here. So we have n to the alpha. So like halfway would be k, the sparsity is square root of n. And on the vertical axis, we have the signal strength, n to the minus beta. So as we go up, the signal gets weaker. Okay. Now, is this feasible or not? Basic question. And this was studied in great detail in a 2013 paper of Berthet and Rigolet. And so they were able to derive the following characterization, where there is a sharp threshold here, this theta statistical, which scales like k log d over n with a square root over the whole thing, demarcating the boundary between impossible and possible. Okay, so this is information theoretically possible. Above this, the signal's just too weak, it's hopeless. Below this, things are in principle feasible. Now, of course, in practice, you care about efficient algorithms, and they did. And they observed that all the efficient algorithms they knew of, meaning solvable in polynomial time, typically one's interested in faster than just some huge polynomial, but polynomial is a crude guideline. They required a stronger signal strength, so square root of k squared over n. So the k has switched to a k squared, it's much stronger signal. And there's a gap between what's efficiently solvable and what's impossible. Now, it's unclear if this gap is fundamental, maybe if better algorithms exist. And that was their goal in a second 2013 paper, where they showed that actually, under a natural complexity theoretic assumption, there is a computationally hard regime here, where no polynomial time algorithm can solve this problem, even though in principle it's information theoretically solvable. So there is the information there, it's just hard to get at. And this phenomenon is called a statistical-computational gap. And it's at the core of high-dimensional statistics nowadays. Okay, so this diagram is still incomplete. There's white regions, and there are various other regions that one might wish to find algorithms for. So I just added a little green bar there that came from a paper of Feige and co-authors. And then there have been many other algorithms with various features, robustness, and so forth, better runtimes, various other features to better understand this easy or feasible regime. And then in a couple of recent papers, we filled in the remainder of the hard regime. So this more or less completes our understanding of sparse PCA. And on one hand, this is a fortuitous and happy scenario where now we understand this problem, but this should be troubling. This took a decade of work by a ton of people just to understand this one problem. And in actuality, there are dozens and dozens and dozens of problems. Many of you probably either work on them or are familiar with some of these. And understanding one of them is good, but it's quite overwhelming to try to think about all of these at once. Okay, so the sort of high-level motivating question for this talk and for this line of work is, how do we systematically go about producing a theory for understanding the feasibility from the computational and statistical side of these various high-dimensional statistics problems with some sort of underlying combinatorial structure. One particular motivating question that I want to get kind of stuck in your head is, what would it even mean to say that a set of problems each have a hard regime for the very same reason? Okay, what would it mean for these to have a hard regime for the same reason? And the answer that I'd like to advocate for is, if there is some root problem, in our particular case, it's going to be what's called the planted clique problem that I'll introduce in a moment, that if one assumes is hard in a certain regime, and let's say there's good evidence for it, and if all of the hard regimes for these other problems are a consequence of hardness for planted clique, well, that would be a pretty satisfying understanding. That would tell us that, well, they're all there because somehow there is an instance of planted clique living inside of them. All right. Good. So that's going to be the high-level objective of the talk is to advocate this way of thinking and to prove some results in this direction. Okay, so let me step back for just a second and spend a few minutes talking about, in a sort of more well-rounded way, what are the broad objectives of this field. So like I said, we have all of these dozens of, and really quite a lot of various high-dimensional statistics problems that have typically garnered attention from people in subdisciplines, deriving algorithms for them, trying to understand when they might be hard statistically, hard computationally, and so forth. And so at large, this field is trying to predict the computational data limit for such problems and give evidence for them, strong evidence ideally, to find optimal algorithms, where now one can actually understand what optimal means for computationally efficient algorithms, because it's no longer necessarily the information theoretic optimal that's achievable by brute force algorithms. There are various associated phenomena that are quite interesting and intriguing in these problems. Structurally, what's happening that makes them hard or easy, things like this. And like I've said a few times by now, if we may dream, we might hope to understand relationships between these problems as opposed to studying each problem in isolation. Okay, now there have been two high-level approaches to understanding these questions, and both of them have attracted quite a lot of energy by researchers. The first is to study specific classes of algorithms. So traditional classes of algorithms in complexity theory are things like bounded depth circuits, things like this. These days, people are very much interested in hierarchies of semi-definite programs, for instance, the sum of squares hierarchy and other such hierarchies, statistical query algorithms, and so forth. And the question is, well, let's see how well this class of algorithms does on the problem. And this will give us insight, at least into the limitations of this class of algorithms for this class of problems. Second approach is this average case reductions approach. And here we directly relate problems of interest. This is the traditional complexity theoretic approach that probably all of you have seen when producing reductions between NP-complete problems, for example. The difference here is that these problems are probabilistic in nature, and so one needs average case reductions, which I'll describe, as opposed to worst case reductions. Okay, so as far as limits for classes of algorithms, here's an incomplete list of classes of algorithms and a very incomplete list of papers associated to each of these. And like I said, for instance, with sum of squares, one tries to understand how well can sum of squares algorithms do for a particular problem, like, let's say, sparse PCA. One would then show that when the signal strength is below some threshold, let's say the computational threshold, the class of sum of squares algorithms of a certain degree that therefore run in polynomial time cannot solve the problem. And this gives evidence for the problem genuinely being hard. Now, of course, there are tons of classes of algorithms, and a priori one has to understand hardness for a problem within each class of algorithms, because if it's hard for sum of squares, well, it may not be hard for statistical query algorithms, and so forth. There's another related approach here, which is energy landscape barriers and sort of ideas from statistical physics, where one tries to understand structural properties of the problem as opposed to directly algorithmic behavior. Of course, these are related because local search and gradient methods and so forth struggle when there are energy landscapes that look kind of very jagged and so forth. And this has also been a popular approach. Okay, now, like I said, this is an incomplete list of papers. If you have a paper in this and you want me to include it in this bibliography, whatever reference list, please email me. I'll be happy to. Sorry if I missed your paper. Okay, there has also been this complementary approach of average case reductions, and there have been a slew of papers in this direction as well, but somewhat more limited. Okay, so the plan for the talk is I'm going to quickly motivate the average case reductions approach in a little bit more detail and explain how it fits in. I'm going to talk about the plan-to-clique problem, which is a specific problem of interest. It's sort of the canonical problem. I'll talk about a generalization of plan-to-clique that we introduced that's called secret leakage plan-and-clique. Then we'll develop some reduction techniques to map one problem into another, in particular secret leakage plan to clique, into robust sparse mean estimation. And then finally, we'll give a sketch of the reduction to mixtures of sparse linear regressions. And so these are just two problems that are intriguing and are sort of central, have been studied significantly. And I'll talk about how this fits in with the more general theme, sort of as we go. Okay, so average case reductions. So what is an average case reduction? So in the context of a decision problem or a hypothesis testing problem, we want an algorithm that runs in polynomial time. Let's call the algorithm A. And A is going to take an instance of a problem, P, either under H0, which you can think of as the pure noise instance of the problem, like in sparse PCA, the data was just isotropic Gaussian, or from the alternative hypothesis, H1, in sparse PCA, the data had this spike in its covariance matrix. Now, the algorithm doesn't know which of these is the case, but in either case, we want to map to some other pair of distributions that correspond to the sort of pure noise and the signal distribution for some other problem P prime in total variation approximately. And so little of one here means that the output of the map is close to the desired canonical distribution P prime in total variation that decays as the problem size grows. Okay, now why is this a good thing? Well, if somebody comes along and says, hey, I have an algorithm A prime that solves problem P prime, well, that's quite good, because then if you have an instance of the original problem, you don't know whether it's the null hypothesis or the alternative hypothesis. You don't know if it's pure noise or if there's signal. Let's say that there happened to be, that it was a signal case for P. Then you can apply your algorithm A to transform the problem genuinely into an instance of P prime. Well, it's an instance of P prime, so the A prime algorithm will then solve it. And that therefore constitutes a solution to the original problem. So put another way, if A prime runs in polytime, then so does the composition, and the composition solves the original problem. So this sort of algorithm that transforms an instance of problem P to a problem P prime, what it does is it allows you to convert algorithms from P prime to a problem for P. Now, another way to think of this is that a reduction is transforming one problem into another while preserving whether or not it can be solved in polynomial time. Okay, so does this make sense? If there are any quick questions on this, I'd love to answer them, because this is sort of the basic object that we'll be investigating in the talk.
There are no questions in the chat. I have a quick clarification question. So in the very beginning for sparse PCA, when you showed the red region that is hard, what do you mean by hard? Does it mean NP complete, or what does it mean?
Perfect question. Yeah. So it does not mean NP complete. I wish it meant NP complete. We'll see in a brief moment what it means, but you can take it to be something analogous to NP completeness. Okay, so in particular, what I'll say at this moment, and will become clearer in a few slides, is it means computationally hard, but feasible information theoretically. Okay, so the limitation is not one of, is there enough information in the problem? It's that the information is there, but it's really hard to extract. And the only algorithms that we know are brute force search algorithms. And indeed, there are complexity theoretic barriers to efficiently solving the problem. And so we'll see in a more precise way what that means, but that's perfect. Thank you for the question. Yeah, so I mean, maybe another way to answer the question is the whole focus of this talk is instantiating what does that mean, hard. Okay, so maybe just to reiterate a point that I should have made on a prior slide in terms of restricted classes of algorithms. One way to think about this hardness is, well, we tried really hard and none of the algorithms that we came up with could solve the problem in that regime. The more people try and the more algorithms seem to not work there, well, you get some more and more evidence that it's hard. But is that fundamental? Can someone smarter come along and come up with a better algorithm that actually just works there? And so that's what we're trying to understand, is this sort of phase diagram and giving rigorous evidence for these phase transitions. Okay, so this is
a
what's
couple of
that?
questions in the chat. Shane, do you want to go ahead and ask your question?
Okay, yeah, thanks very much, Siva. Yeah, I was just curious about the total variation way of measuring distance. So it makes sense, the supremum error across sets. Is there any way to relax that? Because it's quite a strong measure.
That's a great question. Yeah, so there's good reason to be using total variation here. And the reason is that if one considers the type 1 plus type 2 error in hypothesis testing, so false positive plus misdetection, then the error probability of algorithm A prime here will then transfer to an error probability for the original problem, where the extra error is what's sort of lost in this conversion. And so total variation plays a fundamental role in hypothesis testing as the best error probability that one can achieve. And so that's why it enters here. But you're completely right that one can relax total variation in principle. For all of the applications where we've been able to come up with reductions, we don't see any benefit to doing that, but in principle, there could be some benefit. Yeah, so terrific question.
Thank you.
Okay, quick follow-up. So I think I understand what's going on, but I felt like this definition does not seem to exploit any underlying symmetry in the problem. That it feels like you want your distance measure to be up to equivalences under any symmetry in the object you're measuring, but is it that it's disappearing because you're?
Yeah, it's a good question. I mean, so let me know if I answer this. So at the moment, all we have is we have two probability distributions, and we're mapping them to two probability distributions. Okay, so you're given as input a random variable drawn from one of the two probability distributions. You don't know what its distribution is, but you just have some data matrix, and so now you apply a randomized algorithm or a Markov kernel, however you want to think about it, and it transforms the input distribution into some output distribution under this randomized mapping, and the objective is just to have the correct distribution at the output. Now here there are just two distributions, so there's no symmetry inherent and so forth. Now, in specific instances, H1 might be the uniform mixture of, for instance, the spike covariance model for sparse PCA, the uniform mixture over k-sparse vectors of a certain form, or things like this. And so there would be symmetries inherent in the H1 distribution. But at the moment, it's a bit abstract.
Thanks.
Perfect.
Yeah, just have a quick clarification question. I think you may already answer that, but is this pair of distribution P sub H naught and P sub H1 considered a input to the algorithm A, or is it just the realized instance that is the input to algorithm A?
That's actually an important question, so I'm glad you asked it. And we'll see in a moment like specific instances of reductions, and so I think all of this will make more sense. But this is good to clarify. So the algorithm gets as input, let's just say, a matrix of numbers. Mm-hmm. So that would be a random variable from the distribution, right. And it's actually very important that the algorithm actually doesn't know whether this random variable was drawn from pH0 or pH1, because that's what the sort of task is to figure. That's the inherent problem, is to decide, is the random variable from this or from this. And so the algorithm, in converting from problem P to problem P prime, takes a random variable X and outputs a random variable Y, where Y now has distribution P prime H0 if X had distribution PH0. Y has distribution P prime H1 if X had distribution PH1.
But does A know it's just this pair that is being considered? Could there be some other distributions other than P sub H naught and P sub H1?
Oh yes. So as designers of a reduction, we can design A with the knowledge of these are the two distributions that are going to be input.
I see. But the polytime is in the realized instance.
The polytime is in the realized instance, in the random variable. That's right, in the size of the instance. Yeah, and typically we'll see it'll be linear time or quadratic time. They're the sorts of reductions we come up with are fast. Okay.
Okay.
Perfect. Thanks. Yeah. Thanks for the question. Okay. Good. So let me briefly just outline what are some of the nice things about average case reductions. In particular, relative to studying restricted classes of algorithms. So first of all, reductions transfer fine-grained runtimes. If the reductions themselves are, say, in linear time, then the composition that we alluded to on the previous slide that gives you the algorithm for problem P, that runs essentially in the same time as the proposed algorithm for problem P prime. And so one can really understand in a fine-grained way the relationship between runtimes for different problems. Okay, now much more importantly than this first point, which is really just an aside, if one wants to understand computational hardness for these problems, it suffices to consider the root problem. Why is that? Well, if there is some hardness conjecture based on restricted classes of algorithms for some root problem, like planted clique that we'll describe in a second, and then there is a reduction to the target problem, well, one concludes that the target problem is hard for that class of algorithms, at least as far as polynomial time solvability is concerned. Now, if there are reductions from the root problem to many other problems, then that's really nice because one then doesn't have to study the restricted class of algorithms for every single problem individually. One can just really understand well the root problem. And so along the same lines, if somebody comes along with a better class of algorithms next week, one doesn't have to separately study every single problem for this new class of algorithms to see if the new class of algorithms maybe does better than one had previously thought. One can just study the root problem, and that's it. Now, for these reasons, reductions go together, very much complementary to the restricted class of algorithms and the structural sorts of understandings that people are working on. It's not that reductions are better, they're just something quite different. And the reason is it raises the stakes for understanding these source problems, the root problem, because now you get a lot of bang for your buck if you get some new insight into what's happening there. And so the various work of a broad set of people is only elevated in importance when one has reductions. Okay, good. So let me describe planted clique. This is sort of the canonical problem of the flavor of problems that I'm talking about. And many of you have seen this problem, but if not, it's really nice. It's quite intriguing. And essentially the problem is as follows. One has an Erdős-Rényi random graph with edge probability half on n vertices. Okay, so that's a purely random graph. And then somewhere a clique on k vertices, so a fully connected subgraph on k vertices is placed. Okay, now the task is to either find the clique or detect that it's there in the first place. And obviously you're not told the index set of the vertices on which there's a clique. Another way to think of this is you could apply a random permutation to the vertices. So now the clique position is uniformly at random over all k subsets. And that's the problem. Is there a clique in there? Look at the graph and figure it out. Okay, so in terms of hypothesis testing, we can think of the null hypothesis as there's a purely random graph. The alternative hypothesis, there's a clique of size k, its position is uniformly located. Okay, so these are two probability distributions on graphs. You are given a random variable, a sample from one of these two distributions, and your goal is to decide which of these two is the case. So this problem has been very well studied. A simple exercise in the second moment method will show you that the largest clique in such a random graph, an Erdős-Rényi random graph, is of size 2 log n. And so one can deduce from that if I placed a clique that's bigger than 2 log n in the graph, well, you can detect it. Why can you detect it? Well, you can just do a search over all size 2 plus epsilon log n vertices. If you find a clique that's of that size, it's extremely unlikely that it occurred by random chance. And so you'll say, aha, I found the clique that you put in there. There's no way that that happened by pure chance. Okay, so that's the threshold for the information limit without regards to computation. What about computationally efficient algorithms, polynomial time algorithms? What's known, and the best algorithm was introduced in 1998, is that if k is of size square root of n, then the clique is detectable in polynomial time. So this is based on a number of different algorithms, starting with the spectral algorithm in the late 90s. And the first thing to notice is that this threshold in the size of the clique that's detectable in polynomial time is exponentially larger than the information theoretic limit. So it's massively bigger. What about cliques that are smaller than square root of n? Well, despite a significant amount of work by a lot of people, zero progress has been made on efficient algorithms that are finding cliques below size root n, and so it's conjectured to be computationally hard. And in the last decade especially, there's been a real push to understand and get evidence for this conjectured computational hardness. So to show various properties of the problem that seem to happen, for instance, overlap gap property is a structural property that Gamarnik and Zadig found to hold at the root n barrier that's saying, aha, something really different is happening here. And a number of other papers, most of these other references here, have studied restricted classes of algorithms and shown that powerful classes of algorithms cannot solve the problem when the clique size is below root n. So all of these give evidence for the problem genuinely being hard and support this conjecture. Okay, so this is the planted clique problem, and this is the planted clique conjecture, that it's hard when the clique is smaller than root n. And I'll just emphasize at this point a bit of terminology, average case, because people often ask, average case just means that the input is drawn from a distribution. So unlike the NP theory of Karp and Cook and others, which is a worst case theory, the sort of complexity theory that's relevant here is average case with probabilistic inputs. Okay, so reductions, there has been work for reductions for statistics problems in the last decade, and I gave references a few slides ago, but all of them suffer from a key limitation, which is that they map from planted clique to a problem that superficially looks very much like planted clique itself. They look like some submatrix signal that's sparse plus independent noise. And so this, essentially looks like the adjacency matrix of planted clique. So structurally, there's not a fundamental transformation that's happening in the reductions. You could argue that they're largely cosmetic to varying degrees. The cosmetics are, of course, quite important, but nevertheless, there's an intriguing question, which is, can reductions map and relate differently structured problems that have significantly different underlying combinatorial structure? So that was really the motivating question for us, and we sought to address it in part in this work. And our answer is that yes, reductions can relate differently structured problems, but planted clique does not seem like the right starting point. Okay, so the goal of this talk, at least in what's left of it, I'll introduce a generalization of planted clique, which is really just a small shift in the definition. It's called secret leakage planted clique. And then I'll describe at a high level, give a sketch of reductions to a couple of different problems that have very different structure from planted clique. And we'll give as many details of those as is possible. All right, so here's a schematic of the web of reductions that we obtained in this paper, starting from secret leakage planted clique. We're able to reduce to all of these problems in this diagram, all of which have quite distinct structure from the sparse submatrix plus noise form. Obviously, this is a lot, and I will not be able to touch on most of this in a short talk, but we'll focus on a little bit of it. And one small remark is that here, secret leakage planted clique that I'll describe is a sort of a unifying assumption that's sort of conceptually useful. Instead, one could think about a k-partite hypergraph planted clique, which is just an instance of secret leakage planted clique, and start with that as the hardness assumption and derive the same web of reductions. Okay, so here's the bit of the diagram that we'll focus on, and we'll see how much of it we can actually get to. Okay, in particular, down there at the bottom is robust sparse mean estimation, the problem I mentioned early on, and the second problem, mixtures of sparse linear regressions. All right, so what is secret leakage planet clique? Well, remember planet clique. Planet clique, the question is to decide between a pure random graph, Erdős-Jenny with edge probability half, or such a random graph with a uniform at random planted K clique. Now, if K is less than root n, then it seems to be hard. Okay, that's the planet clique problem, the planet clique conjecture. So we're going to make what turns out to be a technically convenient modification. What is the modification? The n vertices are going to be partitioned into k parts. So there are k blobs here of vertices, each of size n over k, so the same size. And the clique position is going to be constrained to have one vertex from each part. So you could ask yourself first question, which is, well, how different is this really from ordinary planted clique? We can think about it for a second. Well, this is sort of a balls and bins question. If you were to randomly select a clique, you would randomly one by one select vertices. You could think of that as tossing balls into the bins. And you might ask, well, how many of the bins actually have two or more balls? In other words, how many of these partitions would have two or more vertices? Typically very few of them. This is a classic exercise. And so you can convince yourself that actually this distribution over cliques in certain ways isn't that different from the original planted clique distribution where all k subsets are allowed. Of course, here there is, though, a slight constraint on the position of the clique. All right, so it's not that different at the high level from original planet clique, and the conjecture that we make is that its threshold doesn't change, and we substantiate that conjecture in a couple of ways in a moment. One other remark is that it's probably, it's probably impossible to tell at this point why this small restriction on the structure or the position of the clique would be useful. And we'll see in a little bit how this added structure is useful for reductions. All right, so this is just one example of how we might want to constrain the planted clique problem. There are three others that we use in the paper. For instance, we could have a bipartite instance of the planted clique problem. We could have a bipartite instance of the planted clique problem, where again, there's this constraint on the position to be consistent with a partition. And then there's also an S uniform hypergraph version with a K partition constraint as well. Secret leakage planted clique is a formulation of the problem that captures all of those, it turns out, as special cases, and one can deduce the conjectured hardness for those from one general conjecture for secret leakage planted clique. So it's a unifying principle. So what is secret leakage planted clique? The way to think of it really is just that the clique position is chosen according to some distribution rho as opposed to uniform at random. That's it. And again, this is placed now in an Erdős-Jenny random graph. Okay, so that's secret leakage planted clique. So one question I always get is, well, why secret leakage? Well, you could think of this as having a little bit of information about the position of the clique. Rho you might think of as the posterior distribution on the clique, given a little bit of information about it. So the information might be that there is one clique vertex in each partition. That would be the first example that I described just above. Okay, so all four of the earlier examples can be reduced to from this general secret leakage planted clique formulation for various choices of rho. Now, it should be clear that the choice of rho determines whether this problem is going to be computationally feasible or not. If rho is deterministically placing the clique on vertices 1 through k, well, then there's no algorithmic problem at all. The clique position is deterministic, and it's easy. On the other hand, if rho is uniform over all k cliques, well, then one has the original planted clique problem and the associated conjecture that it's hard up until clique sizes of square root of n. So the distribution over cliques matters a lot. And a conjecture for when the problem is hard and where that threshold is can be derived from understanding how well do restricted classes of algorithms do for this problem. And so we analyze this for low degree polynomial tests and statistical query algorithms in certain contexts. And the high level picture is that a certain property of rho that corresponds to an overlap distribution. So you draw two independent cliques according to rho, and one looks at the probability mass function of the overlap between S and S prime. Depending on how fast that decays, one gets a conjecture for whether that problem is hard for that rho or not. Okay. Good. So this general conjecture, won't be particularly, we won't use it in this talk, aside from that for those instances above, one gets a very concrete conjecture for where the threshold is between computationally feasible and infeasible. And mostly this is just to convey the high level point that there is a natural conjecture for the threshold between feasible and infeasible, depending on this rho. Okay. Good. So any quick questions at this point before I dive into the reductions that I promised?
So I think the computer is acting up. So I'm going to take over for a minute. David has a question in the chat. So David, maybe you can go ahead and ask.
Sure. So yeah, this is I guess one question would be, when we talked before about the, above 2 log n, that's like the typical clique, so it's not going to work. I guess at a high level, this is posited on you getting only kind of one sample from the random graph, and that planting a clique would still maybe change the distributions of the number of cliques a little bit or something like that. And so is there kind of an analogous theory here about if you actually, in some sense, were seeing many draws from that random graph? Does that make sense?
This is a perfect question. Yeah. So in fact, one can in general consider all of these problems that have a single sample. One can consider multi-sample versions, and where you would, for instance, like you say, fix a clique position and then observe some number of graphs sampled IID with that same clique placed. And it turns out that for blended clique, there's a very nice story, which is that there's a full equivalence between multi-sample version and a single sample version. And one of the directions is easy. It turns out that if you have a bunch of IID samples sort of with independent noise, the optimal thing to do is just to AND all of those. So you keep an edge only if it's present in all of the copies. And so clearly that keeps your clique because the clique position is the same. And then the IID nature of the noise will quickly reduce the edge probability outside of the clique. But that can be shown formally. And in fact, there's a reduction in the other direction, where if one starts with one instance of planted clique, one can clone that, so to speak, and produce many instances where the noise level has gone up within each of those instances. And so it's a terrific question.
And then maybe one more question following up on what Wayna had asked before. So since we're talking kind of formal complexity polytime here, I know one thing that I've struggled with in very different settings is this notion of, well, here you're kind of dealing with real numbers, maybe. And then following up on what Wayna said, if we take polytime reduction in a literal sense, then classically this was in principle backed up by Turing machines and all this kind of stuff. But if those distributions have exponentially or even infinitely large descriptions, like these null distributions, then is there a formal theory to what a polytime reduction is? And can you boil it to a Turing machine-like concept of it inputs something somehow and does something somehow in a very mathematical sense? Or yeah, what's your thinking?
Yeah, no, it's a good question. Yeah, so it is something that that one should worry about a little bit. And to make everything formal with respect to the Turing machine that have randomized, random bits and so forth, one should look at quantizations of real numbers. And so in general, one can go to log n bits of quantization and so forth. There's actually a paper of Zhongming Ma and Yihang Wu that's cited in our papers, I think 2014 paper or 2015 paper in Annals of Statistics, that it goes through this very carefully in terms of these bit quantizations and so forth. So we don't worry about it in our papers, but all of the sort of real arithmetic can be made precise in terms of its complexity. It's a great question, though. All right, cool. So I see that I'm running a little behind schedule, sort of my scheduled plan in terms of what I was going to cover, but I really do want to cover a significant portion of the techniques, because that's really the meat. That's kind of the cool part, where one gets to see, here's a problem described by one probability distribution, and you're transforming it to get a completely different problem. And in many ways, I think I'm still shocked when I can look at one problem and say, hey, look, robust sparse mean estimation. Yeah, that's actually kind of like planted clique in a very precise way, in a way that's formal and can be made precise. And so I still think there's something a little bit magical about these average case reductions. And I want to try to convey how one does these transformations in a couple of instances. Okay. So good. So there's going to be an associated technique here. We call the technique Bernoulli rotations. But before I get into all that, I want to describe what is robust sparse mean estimation. So you'll have the problem in the back of your head, and that'll guide how we're going to do the reduction. Okay, so this problem superficially, it's similar in flavor to sparse PCA. The problem is estimate a k-sparse vector. So we just have a k-sparse vector, k non-zero entries. The vector is mu in RD within some L2 error gamma from n IID samples, so your data is n samples from isotropic Gaussian centered with mean mu. Okay, so this is how you should think of it. There's some vector mu, and you observe this thing perturbed by Gaussian noise with identity covariance, and you get n samples, and your goal is to estimate this mu. Okay, well, turns out this problem has no statistical computational gap. It's a very classical problem. And if you think about it, because everything's sort of isotropic here, the coordinates themselves aren't really related one to another, and at least up to sort of some constant factor in performance. And sort of, if I want to decide is coordinate 1 in there or not, I should see if coordinate 1 is big or not. And so in general, the optimal algorithm that achieves the information theoretic limit is the efficiently computable thing that looks at the empirical mean and then chooses the k biggest entries in absolute value. And that turns out to be optimal. Okay, so that's sparse mean estimation. We can consider a robust variant of it, where, just to make life a little easier here, oh, I see, there's still a gamma. So let's pretend that we're estimating to within L2 error gamma, which we'll take to be big O of epsilon. And so the setup is exactly the same, but now an epsilon proportion of the samples are corrupted by an adversary. So the prior estimator, which just chose the k biggest entries, is no longer any good, because an adversary can just come along and periodically make some entry enormous, which will disturb the empirical mean significantly and make the prior estimator quite poor. And so it turns out that now there does appear to be a statistical computational gap where the information theoretic limit is the same as before, but the computational limit now has an extra factor of k in there. The algorithms that achieve this computational threshold are sort of based on convex programming. And sort of the basic idea is to try to figure out which part of the data looks like it's been corrupted. It somehow doesn't look very Gaussian. And so then you try to throw it away and then estimate based on the remaining data that looks consistent with the Gaussianity assumption. All right, so there's a gap between what's efficiently doable and what's information theoretically doable with a brute force search. Okay, so the theorem that we stated is that assuming the k-part bipartite planted clique conjecture, so that's a sort of instance of this slightly more structured planted clique conjecture, any polynomial time algorithm for robust sparse mean estimation genuinely requires this number of samples. And so you cannot improve on this computational threshold if the k-part bipartite plan-to-clique conjecture is correct. All right, so this is going to be proved by reduction. And so to guide us, I'll just emphasize that if we're starting from plan-to-clique and we're mapping to robust sparse mean estimation, we sort of have 4 things that we need to do. The first thing we need to do is to map the canonical stochastic model appropriately. In other words, we need to map Erdős-Renyi graphs to Gaussian data. So we need to map Bernoulli random variables on the edges to Gaussians. That's kind of step 1 at a high level. A second thing that needs to be done is to map the hidden structure of plan-to-clique into some sort of hidden vector in robust sparse mean estimation along with the corrupted samples. Third, one can't just introduce noise arbitrarily. One has to very carefully carry out this reduction so there's no loss in signal, so that the boundary between feasible and infeasible actually maps from feasible to infeasible in plan-to-clique to the correct boundary in the problem. So it needs to be lossless in a certain sense, at least up to constants. And finally, robust sparse mean estimation has a whole bunch of parameters. Plan-to-clique only has a couple of parameters. And so, so we actually need to fill out the parameter space when we produce this phase diagram. And so that's yet another challenge. Okay, so with these things in mind, this motivates the 2 techniques that I'm going to talk about. One of them is algorithmic change of measure to address the first thing, which is Erdős-Renyi graphs to Gaussian data. And the second one is the genuinely changing structure from cliques to hidden vectors with corrupted samples. All right, so the computational change of measure that I'll talk about is something that appeared first, to our knowledge, in a couple of papers of Ma and Wu and Hayek, Wu and Xu. And we generalized in various ways in a couple of papers. So now the goal is to produce an algorithm that we call rejection kernel that takes an input, either Bernoulli half random variable, which would be like the non-clique edge in plan-to-clique, and produces a 0 mean Gaussian, or it takes a 1, which is it would be the edge within the clique and produces a Gaussian with some mean mu. Mu is some real number here that's hopefully as big as possible. Okay, so this is a sort of gadget or reduction technique that we hope exists. And it turns out it's actually, one can show pretty quickly that it does exist, and I'll describe it. So we need to say what happens if the input is 0 and what happens if the input is 1. Well, if the input is 1, our hands are tied. We should just produce a sample from normal mu 1. On the other hand, if the input is Bernoulli half, we want to output a mean 0 Gaussian. And so it turns out that if the input is 0, we should sample from 2 times the density of the mean 0 Gaussian minus the density of the mean mu Gaussian. Why is that the right thing to do? Well, you can check that a Bernoulli half random variable gets mapped to the half-half mixture between the 2 distributions. So you get half phi1 plus a half times the quantity 2 phi0 minus phi1. The phi1s cancel, and one is left with phi0, which is the desired output if you have as input a Bernoulli half. So this solves the problem. The issue is that 2 phi0 minus phi1 is not a valid PDF. It, in particular, can be negative. And so here we're plotting the difference of the 2 Gaussian densities of interest, and one can look at this purple line, the 2q minus p, and see that it goes negative. So the way around this technical obstacle is just to truncate the distribution to its positive part. And if the means satisfy a condition that they're fairly close, like 1 over polylog, then the total variation loss is not too significant here. And so one can indeed map from Bernoulli's to Gaussians in the way that's desired in the specification here. Okay, so that's an algorithmic change of measure. It was a little fast, but the high level point is one gets mapped to a Gaussian with a positive mean. Bernoulli half gets mapped to a zero mean Gaussian. Okay, now here's the kind of the main technical sort of algorithmic routine in order to change the structure of a planted problem. Okay, so the goal is, and we'll see just in a moment how this immediately gives rise to a reduction, is to consider the following much simpler setup. We have a vector of n bits, of n01 bits. All of the entries are Bernoulli half, except for one of its entries in the ith position is fixed to be 1. Okay, and so we call this the planted Bernoulli of I distribution. It's just a vector with a 1 in the ith position. And what we want is a Gaussian x that has mean some scalar tau times ai, where ai is the corresponding vector from a collection a1 through an corresponding to whichever bit in the input vector was fixed to be 1. Now, of course, as always is the case here, the algorithm shouldn't know, it gets a random variable. It gets a vector of zeros and ones. It doesn't know which distribution PB of I it actually came from. And so it simultaneously has to map all of the PB of I distributions to the corresponding Gaussians without knowing which of them was the case. Okay, now A1 through AN are just some design choice. One can fix those and hope to get such a mapping. All right, good. So this is what's desired. And maybe worth emphasizing in the applications, what's important is choosing in some smart way these AI vectors, the means of the Gaussians at the output. And those really are what encode the structure, that those AIs can have some interesting structure. Okay, so I'll briefly describe the algorithm itself. The algorithm is first going to Gaussianize each of these entries independently. And that's just by this algorithmic change of measure. What one ends up with is a Gaussian with identity covariance and essentially zeros as the mean, except for one of the entries that corresponds to whichever entry had a 1 in the input is now going to have some elevated value. And so this whole mean is just the standard base, the ith standard basis vector. And so if you think about it, then, well, we want to now have mean AI. And so we can just multiply this whole vector by the matrix whose columns are these AIs. And that'll just pick out the ith column. And so this will produce something with the correct mean, but unfortunately it has the wrong covariance. And that's just because the covariance of a Gaussian when you pre-multiply by matrix ends up having that matrix living inside the covariance. And so now there's a second step in order to correct the covariance and in order to whiten the signal. Okay, so this second step just cancels the induced correlations that was needed in order to achieve the correct means. And so at the end of the day, we've produced a vector that has some sort of structured mean AI. All right, good. So I realize I'm a bit over time, but I just really want to get to the reduction because we're quite close and we can see how all the ingredients fit together. So sorry for being a little bit over time, but okay. Okay, so remember this is robust sparse mean estimation. You observe n samples from some Gaussian and then there's epsilon proportion of corrupted samples. We get to choose the adversary. The adversary can be anything in robust sparse mean estimation. And if we're trying to show hardness, well, we can choose it to be whatever we want. And we're going to choose it to be some other Gaussian with a slightly different mean. And so we're going to consider robust sparse mean estimation with a particular structure for the mean, which is just uniform on some index set S, and then the outlier distribution has some other uniform on same index set S with a different value. And so a cartoon for the data looks as follows. If we consider a D by N matrix of the data, the samples are arranged as columns. And so most of the columns just have some value X for the mean in the subset of indices in S, and then some epsilon fraction of them have value Y. On top of this, of course, there's added Gaussian noise. There's standard Gaussians added on, but this is sort of a cartoon for how the data matrix looks like for our specific choice of robust sparse mean estimation. Okay, so now the reduction, we start with some graph problem and map to this. How does that look like? Well, we're going to start in particular with this k-part bipartite planet clique, and the cartoon of it looks like this. And now one really sees why this added structure is useful. It's because we can apply this Bernoulli rotations algorithm, this Bernoulli rotations transformation, to submatrices or subvectors within this bigger matrix. And so the constraint that there's just a single one within each block here, which is really what this structural, the k-partite constraint does, is what allows you to have the valid input for the Bernoulli rotations gadget. And so when applies Bernoulli rotations here, one gets a Gaussian with mean that corresponds to the location of the one within that subblock, and does this to all of the subvectors within this adjacency matrix of this generalized planet clique instance. And now if one just compares this to the cartoon of the robust sparse mean estimation, then we can get a sense of what we want out of these AJ design matrices, these AJ design vectors. Well, we want it to look like this cartoon with mostly blue entries and some red entries. And then there's an added technical condition that the singular value of the associated matrix isn't too big, because there was a scalar there that sort of degraded the signal in that proportion. Okay, so without getting into the details, we want these AJs, this is just based on like pattern matching between the robust sparse mean estimation problem and what we have when applying Bernoulli rotations to subvectors within the planet clique instance. One just does this pattern matching and one gets some desiderata for these AJ vectors, and we want them to be zero sum. We want them to mostly have entries that are X or blue and a relatively small epsilon fraction of entries Y, which correspond to the adversary that we chose. And we have a singular value constraint. Now, due to sort of time, I won't go into the details of the construction, but there's a construction based on combinatorial designs on the incidence geometry of hyperplanes and points in vector spaces over finite fields in this projective geometry. And I won't go into the detail, but there's a sort of combinatorial construction of how to choose these AJs that turns out does satisfy these constraints. I should say a priori, it's not at all obvious that there exist collections of vectors that satisfy the desired constraints. And in fact, for months and months, we had no idea how to find them. But I guess Matt woke up one day and realized that this was the way to do it. So there is a construction that achieves the form that, at least from the cartoon point of view, achieves the desired structure for robust sparse mean estimation, starting with this reduction. And that completes the reduction to robust sparse mean estimation. Alrighty. I was also going to talk about reduction to mixture of sparse linear regressions. I think it's probably prudent to not go into the details there, except for to say that it's maybe quite a bit more involved and actually uses the robust sparse mean estimation reduction as an ingredient within it to arrive at a problem that in some ways has even more different structure than planet clique, than robust sparse mean estimation. And one intriguing sort of gadget within this is a reduction to negative sparse PCA, where the spike is negative instead of positive, and it turns out to be dramatically different in flavor than the ordinary sparse PCA and requires an entirely new reduction, even just for this component of it. All right, so there's here's a sort of cartoon of the reduction. It goes through many steps. There are many other reductions to many other problems in the paper, and I invite you to please have a look if you're interested. So I'll briefly conclude and then state some open problems. So the high level of what we aim to achieve was to show that one can reduce to problems with dramatically different structure than planted clique within this framework of average case reductions. The key insight is to generalize planted clique to secret leakage planted clique, where the clique position is no longer uniform. It has some other distribution rho. And this allows a number of new average case reduction techniques or gadgets to actually work. And they require that they make use of that assumption in a strong way. There are still dozens of problems for which the computational data limit and how information and computation interplay within them remains poorly understood. And we need more techniques for reductions if we hope to relate those to some of the problems that are already well understood. And there's really a ton left to do. There's really sort of a Wild West situation. Like almost anything that you could hope to do in this general field is remains open. And so if you're a PhD student and you're interested in this direction, I encourage you to think about this. And there's really a lot here. It's a gold mine. Here's a few concrete open questions. Maybe I'll just not read through them and just leave them up here while maybe spend a few minutes answering remaining questions. So with that, thanks very much. This has been fun.
Let's thank the speaker. Questions, Dave?
Yeah, so I guess the question I put in the chat, I have a few questions, but I'll start with, so does the corrupter / adversary get to know your algorithm? Like, is this an ordered thing? And does that matter for these reductions? Because I think one thing I was confused about at the beginning was like, the corruption thing seemed to have an extra layer of adversarialness to it, but then that seemed to disappear in some sense. And so, yeah, is there a notion of these adversarial corruptions get to know your statistical thing you're going to do before picking what they're mess up? Is that a relevant, meaningful question here?
It's actually a great question. Yeah, so it's a terrific question. So in general, the adversary can be arbitrary. It just does whatever it wants to epsilon proportion of the samples. And that's a very strong form of adversary. In fact, in that case, the adversary can even choose which samples to corrupt. It can choose that based on the data itself. This is quite a strong adversary. There's an intermediate adversary, which is called Huber's contamination model, where just the data itself is randomly chosen with probability epsilon to be from some outlier distribution and with probability 1 minus epsilon to be from the correct generative model. And so that's much less adversarial.
So, but even in that strong adversary setting, it would seem like they do not know what statistical, they don't know that you're going to do 6 levels of the sum of squares hierarchy, in which case they might want to pick the epsilon n things to mess up that specific technique. So it seems like it's still an oblivious adversary in some sense, or is that not?
Well, if you think about it as worst case over adversaries, then if you were to claim that level 6 of sum of squares solves the problem, it would have to solve it for every adversary. And so then I think you could think of it actually as the adversary knowing what you're planning on doing.
Okay, that I think.
So it's an element, another way to think of it at the high level is that it's an element of worst caseness. So this problem isn't purely average case, actually, as you sort of point out. It has an adversary there that can do just literally the worst thing for you.
Sure, no, that makes sense.
With that said, though, the reduction that we produce isn't making use of that worst case nature of the adversary. We actually reduce to a much more benign adversary, which was this sort of Huber's contamination model with it just has data from a different Gaussian. And so it's a very specific adversary. It's actually pretty natural. And what this shows is that even for this pretty benign adversary, the problem is hard, assuming that this variation on planet clique is hard.
And then a second kind of high level question about the model. So if I understood kind of at a high level how your proof went, it was kind of going under the hood of the probability space of how these distributions were actually being generated. At least it seemed to at a kind of conceptual level, because you were kind of coupling things in some sense, maybe. And then I guess I was a little confused about, like, if these distributions, like if you're getting samples from them, but maybe the distributions are actually high dimensional and complex, do you need to be able to go under the hood there? Or in principle, was this all a thought experiment that they're coupled and you really are you just need the samples? You don't need to generate jointly or something from these distributions, if that question makes sense.
Let me think. So at the end of the day, the reductions are just taking some instantiation of a data matrix and manipulating.
So you never actually have to say, I must construct these two distributions jointly using some common omega or something like that.
Yeah, that's right. That's right. I think that one way to think about all of these reductions and randomized algorithms in general is as a Markov transition matrix, Markov transition kernel. And so to think about that, I mean, you're taking one step into Markov chain. And so it just needs to know the current state. It doesn't need to know the distribution of the current state in order to evolve it one step forward.
Okay, that makes sense. And then the final thing that I'll totally shut up, but I'm just so intrigued by the topic. I need to know, do your conjectures agree with the whole stat physics enterprise? Or is there actually, are there cases where your conjectured kind of thing actually says, no, what stat physics had predicted for some of these things may not be correct?
Oh, good question. Yeah. So our conjectures for secret leakage planet clique, they come from the low degree method for predicting these thresholds, which is a method that asks how well do distinguishers based on low degree polynomials do. Now, those are, I would say, largely consistent with the statistical physics view, but not entirely. For tensor problems and so forth, there are discrepancies, but there are ways to correct that. So maybe the high level, so the quick answer is that we don't disprove any statistical physics conjectures or anything like that, or we don't contradict any. But for many of these problems where we have reductions to from planet clique or a variation on planet clique to the problem, there was no statistical physics prediction in the first place. And so sometimes it's actually quite hard to produce the predictions in these target problems. You know, they're complicated combinatorial problems. It's challenging in the first place. But I will just say it as an aside, one of the primary ways that statistical physics was aiming to produce conjectures for the thresholds was to understand where belief propagation stopped working. And there's an extremely interesting recent paper of El-Alawi, Moore, and Wine from the last Fox that shows that for tensor PCA, tensor problems, basically, BP is never going to get close to the threshold, and one needs to go up the Kikuchi hierarchy, which those of you who studied BP in sort of graphical models course, you might have seen the Kikuchi hierarchy. I myself, I was like, oh, why would you ever do this Kikuchi thing? It's not clear when it's good and when it's not. But actually, it turns out that the Kikuchi hierarchy can sort of emulate what higher degree sum of squares algorithms are doing. And so anyway, I recommend people look at that if they want to understand sort of some of the relationships between the statistical physics predictions and how that relates to sum of squares and the more sophisticated theoretical computer science algorithm frameworks.
I have a question. So in computational complexity theory, there is this whole class of NP-complete algorithms for which the reductions both ways, right? So basically all the algorithms are in some sense similar. So here, do you think that one can possibly find similar reductions to like both-way reductions to other problems? Or do you think that the secret leakage PC is in some sense special?
Perfect question. Yeah, I love this question. So it's actually something we've been motivated by from the very beginning. is to find equivalence classes of problems, just as you say is true for NP completeness. We have some that are sort of kind of semi-obvious. At the moment, we don't have any finished two-way reductions, I would say, that are sort of non-obvious. I guess the second question, so yes, it's a very much a good goal, it's a good objective. So yeah, sort of the second question is secret leakage planning clique going to be sort of equivalent to other problems? And it turns out that the clique structure itself is incredibly fragile. Once you add a little bit of noise and you just have a very dense subgraph instead of a clique, we at least have no idea how to go back to a clique. And there's good reason to think that it's actually impossible to go back to a clique, that maybe I won't get into because it's a little bit longer of a discussion, but I think that there is hope for a secret leakage planted dense subgraph, where instead of a clique, there's a very dense graph that's not a clique, to be equivalent to many of these. It's unlikely to be the actual clique problem.
Got it. Thanks. There are no other questions on the chat, so let's thank Guy again.
Thanks so much, everybody.
We'll end the recording now. If there are any other comments or so, we can chat.